Hello, today we are going to be looking at our fourth video in the Kinetics chapter 14 unit. What we are going to be doing today is we will take those rate laws that we worked on in the previous video and we will start calculating with them. So we definitely need to have our calculators nearby for today. So before we get to plugging in to the rate law, we have to talk about K, the rate constant. So the units for the rate constant will change depending on if we're dealing with a zero, first, or second order reaction. So one of the things that you'll have to do is solve mathematically for the magnitude of K and then also for the correct units. So we have to remember that rate is always change in concentration over a period of time. So your units for rate is always going to be concentration per time. Very often, it's going to be molarity per second, but it could be different units, but molarity per second is going to be our most common. You know, it could be per minute instead of molarity, it could be moles per liter, but it could even be a slightly different version of that. So when you are figuring out K, you will have to figure out how the units work in order to get, say, molarity per second or whichever units you are looking for. You could memorize the units for the rate constant, but I would not recommend doing that. I would just recommend using your dimensional analysis skills in order to figure out the appropriate units. So let's say that this is our rate law. So it would be first order with react to A, meaning that if whatever we do to A, it does that to the rate. So if we double the concentration of A, the rate doubles. If we double the concentration of B, the rate would also double. So it's first order with respect to both and second order overall. All right. So if we know that our rate has to be molarity per second. So let's just rewrite our rate law. Okay, so let's say that rate has to be molarity per second. We're looking for the units of K. A is change in concentration at A, so that's going to be molarity. B is also going to be molarity. So we have molarity per second equals K times molarity squared. So in order to find K, molarity per second divided by molarity times molarity. Now you could leave that molarity squared, but for me, I like to write it out molarity times molarity. It just makes life a little bit easier for my brain. All right, so that would give me, molarity is on the bottom. So per molarity per second as my unit. Now, alternately, you could write it as 1 over molarity and seconds, because that would be equivalent. Instead of molarity, you could also be using moles per liter. But I think that's a little bit harder because then it just introduces a third unit that you have to keep track of. So I prefer to do it in molarity. All right. Now we are going to, again, take a look at each one of those. You could memorize it, or it is easier to just think about the units. So if we have a first order reaction, my equation is, or the rate law would be rate equals K times the concentration of A. Oops, sorry, I meant to write A there. All right, so if my rate needs to be molarity per second, I'm looking for K. Concentration of A would be in molarity. So K would be molarity per second divided by molarity. So the two molarities will cancel out and my units would be per second. So when I have a first order reaction, it's going to be per second or per time if they were measuring in minutes or hours. But again, instead of memorize, just plug it into the equation and let your units work out for you. All right, if we have a second order reaction, then my rate law would be K times either A squared or A times B would also work. So again, if I'm working with my most common units for rate, molarity per second, K times molarity squared, because concentration of A would give me molarity squared. So therefore, K would be equal to molarity per second divided by molarity, divided by molarity. So this is just like the one we did on the previous slide. One of the molarities cross out, and that gives us per molarity per second as my unit. But again, not worth the energy to memorize them, just use your dimensional analysis skills that you all have, because you guys are very good at dimensional analysis. All right, third order reaction would be rate is equal to K times A cubed, or it could be times concentration of A times B times C. Either way, it's going to be concentration times concentration times concentration. So if we're using molarity, it would be molarity cubed. So if I need my rate to be molarity per second, and I have molarity cubed, in order to find K, it would be molarity per second divided by 3 molarities. So only one of those molarities would cancel. So my units would be molarity to the -2, or you could do 1 over molarity squared. They're the same thing per second. So hopefully you see that it is easier to just work the units out off to the side and not bother memorizing them. All right, now we have a great example. So in this example, we are going to tie everything together. We are going to use the experimental data to find the rate law like we did in the previous video. Then, once we have the rate law, we are going to plug our values in to find the value of the rate constant and the units of the rate constant. So first thing we got to do is find the rate law. So pause the video, find the rate law like you did in the previous video. All right, so hopefully you figured out that B is going to be 0 order and A is going to be second order. The reason why, if we look at experiment 1 to 2, A is constant, B is doubling, and the rate does nothing. There's no change, so B has 0 impact on the rate, therefore B is 0 order. Since B is 0 order, we know it's not going to change anything, so then we can look at experiment 2 to 3. A is doubling. Yes, B is also changing, but we know B doesn't do anything to the rate of the reaction, so we really can just kind of disregard B. So A is doubling, we know B doesn't do anything, and the rate is quadrupling, so that is going to be second order, because think about your rate law. Your concentration is increasing by a factor of 2 squared. 2 squared is 4. So my rate law is going to be K times the concentration of A squared times the concentration of B to the 0 power, which that would have a value of 1. So I would just leave that out. So you don't need to write that. You could have gone straight to K times A squared. All right, now what we are going to do is we are going to pick an experiment. Any one of the experiments, it does not matter. We are going to plug the values in, solve for K, and solve for the units of K. I normally pick experiment 1 just because it's at the top. So you plug in the values from there. So that would be 4 times 10 to the -5th. and that is molarity per second equals K, that's what we're looking for, times the concentration of A, 0.1 squared. So now we just plug this all into our calculator. So we are going to have 4 times 10 to the negative fifth divided by 0.1 squared. And that would give us 4 times 10 to the negative third. And honestly, I shouldn't have even used my calculator to do that. And we want 2 significant figures. All right, so that's going to get me 1 point for the value of K. Then I also need to determine the units. Personally, I kind of like to do that off to the side. So I know my rate has to be molarity per second. And concentration is molarity, and that was squared. So I would get molarity per second divided by 2 molarities, and that would give me per molarity per second. So then I would write that in here, and that would give me my final answer. This would typically be at least a 3-point question, 1 for the rate law, 1 for the value of K, 1 for the units of K. It could be more than that if you were required to explain how you got the rate law. All right, we have one more example here. So we are going to do everything again. We are going to use the data to find the rate law. Plug in your values to find the magnitude of K and also the units of K. I would love it if you would pause the video and try this independently and then come back to check your work. All right, so hopefully you found out that it is first order with respect to the S2O8 2 minus and first order with respect to the I-1 ion. So if we look at experiment 1 to 2, the S2O8 stayed constant while the I- decreased by a factor of 2 or got cut in half. The rate also got cut in half since they're doing the same thing. That's first order. If you want to put in the 1 here, you can, but obviously you do not need to do that. With experiment 2 to 3, the I- was staying constant, but the S2O8 ion was doubling and the rate doubled, so they are doing the same thing. So that is also first order, which would make our reaction second order overall. Then you take the data from any one of the experiments. I usually use experiment number 1 because it's at the top, and plug my values in to solve for K. All right, I plugged in experiment 1 and I got 0.08 for the value of K. Then when I worked on my units over here, I took the rate law units, divided by the 2 molarities to get per molarity per second. Now I did leave it as 0.08 with only 1 significant figure because this does only have the 1 significant figure. So again, you find the rate law, then you just plug in, do the math, and work out the units. Also, the larger the value of K, the faster the reaction is going to go. And K is going to be dependent upon temperature and also will be an indication of the activation energy of the reaction.